Welcome to this tutorial series that will cover the theoretical background that's required to analyze CFD or wind tunnel data with Epsilon. In this first session, I will present the classical aerodynamic analysis methods. In particular, we'll cover the four classical methods, which are near-field, far-field, land vector, and power balanced. For each one of the cases, I will present the formulation, the drag breakdown associated to the formulation, and the applications and limitations, except for power balance, where the just basic introduction and applications will be presented. So let's go for it. Let's get started with the near-field method. And the near-field method is an aerodynamic analysis method that's only related to the body surface, and in particular to the forces acting upon this body surface. So the formulation, basically it considers a standard reference system X, Y, Z, X always pointing downstream, Y pointing to the right hand side of the body, Z pointing upwards. And then if you consider a surface of an aircraft, you should consider an element of surface marked here with this stripe. And then in order to obtain the total force acting upon the body, you have to take into account the force generated by the pressure acting normal to this element, and also the friction force acting tangential to this element. So if you perform an integral on the total surface SB enclosing the body, you will obtain the total force acting upon that body. And that's the basis of the near-field method. It's called near-field method because you are taking into account the forces acting upon the body surface. That is the near-field method. And as you can see, there are two components of this equation. One is related to the pressure force and the other is related to the friction force. So this is the basis of a drag breakdown. We will talk about that later on. Now we will just decompose the total force. This is a vector. We'll decompose that into two components. The vertical component along the z-axis is the lift force. As you can see, the normal vector acting on each surface element. Here is a vector. Now we're just taking the vertical component for the pressure and friction component. And when you integrate that, you obtain the lift force. And in the same manner, if you take into account this time only the x component of the normal vector of the surface, you will obtain the pressure and friction force acting along the x-axis, and that will give you the drag force. Then, as I mentioned before, the near-field formulation contains two terms, so this will allow me to perform a drag breakdown. So this is the drag equation that I presented you before, that takes into account only the x component of the normal vector acting on each surface element. And then the pressure term along the x-axis will generate a pressure drag, and in the same manner the friction term acting along the x-axis will generate a friction drag. So this is a very first drag breakdown, that is the total drag is decomposed into pressure drag and friction drag. To understand what's behind this breakdown, let's take into account the case. There's a rectangular wing with aspect ratio 8, NACA 12 airfoil, and it will be shown at 10 degrees and Mach 03. So this is the case, CFD data that you can actually find in our website of Epsilon. You can actually evaluate this near-field equation, and if you show the friction force acting along the x-axis, that is this term, which is evaluated point by point at each point of the surface, you will realize that the friction force is higher nearby the leading edge, and that's where the velocity is higher. So basically the friction forces are related to the local velocity around the surface. So in order to reduce the friction drag, you have to deform the geometry in order to reduce the local high velocity. And that's the basis of the laminar airfoils. Laminar airfoils are geometries that reduces the over velocity nearby the leading edge and provides a more smooth velocity increase all along the chord, and this reduces the friction drag. Regarding the pressure drag, this is what you get when you evaluate this term at each point of the surface. And as you can see, this term of pressure drag is basically linked to the pressure coefficient distribution. So it's easier to visualize the pressure coefficient distribution and then to try to understand. For example, here in this region you have some all negative, which means there's a local low pressure, and then since this is at 10 degrees and this generates almost negative, that's a suction here, suction pointing towards the downstream, it will generate drag, and that's why drag in this region here is positive, because you have a pressure force acting on this part pointing to the left hand side, which means this is a drag. So it's quite practical to analyze the CP instead of this field for this particular case. But let's keep in mind that from all the drag, most of the drag comes from friction drag, unless you are analyzing a high angle of attack case. One of the interesting applications of the near field method is that once you compute the parameters acting on the surface, for example, I can compute here the lift force attributed only to the pressure component, you can evaluate that at different span-wise stations all along the spans of the wing, and that will give you, for example, the distribution of lift. And you can do the same, for example, to get the distribution of drag. And of course, for drag, you can break down this distribution of total drag into pressure drag and friction drag as well. And in the same manner, lift can be broken down into pressure and friction. This is not quite practical because the lift generated by the friction is marginal, so it can be ignored. It's mostly pressure contribution. Indeed, in this case, it's very clear that this lift distribution, this reduction of lift, is associated to the CP distribution that we have shown below. But this peak here is related to this low pressure region here generated by the vortex that goes over the top of the airfoil. So it's quite practical, this approach, to do a first guess of what's generating this lift distribution based on what we get at the surface of the body. But the problem is that when you start analyzing more complex geometries, doing such analysis is not that straightforward. There are a lot of difficult things to take in consideration in order to perform comprehensive analysis. We'll talk about later in another videos. So now we should stick to the theory itself. So one of the most interesting applications of the near field method, in fact this is the most direct application, is to establish what's called the drag characteristic curves. So basically, for a given case, in this case a 2D airfoil, NACO 12 airfoil at a given Mach number, you can sweep the angle of attack, and for each angle of attack you can obtain drag value, and the total drag value obtained by near field method can be broken down into its pressure and friction components. So this is the very first drag breakdown obtained by the theory, the aerodynamic theory. Basically, it allows you to determine drag, which is a practical thing, but also to decompose it in order to understand the physics lying behind. This gives you some ideas of what to modify in the geometry in order to reduce each one of these components and ultimately to reduce drag. That's our measure objective. The only problem of the near field method is that let's say you apply this or you obtain these characteristic curves for a 2D case or a 3D case, in this case a rectangular wing with the same airfoil. As you can see, the drag curves have the same shape roughly. There you have the black curve decomposed into this decreasing blue curve and increasing red curve that corresponds to friction and pressure respectively. So if you take a first look at the plots, you cannot differentiate between 2D and 3D case immediately by just taking a direct look at the plots. That's a problem. That's a problem because we know by our understanding of physics that the 3D case have a completely different physics. So what I expect to have is a completely different plot. Instead, what I have is roughly the same plot with different values of drag. So this is a problem. We should get a aerodynamic analysis formulation that allowed me to put that into evidence, that is to put the physics into evidence. Here, the three-dimensionality of the flow is hidden inside these terms. I cannot take away the 3D aspect. So this is one of the drawbacks of the near-field method. However, it was the very first method. It is still used today. It's quite practical, especially to obtain reference drag values and to start understanding how it behaves a given body based on the pressure forces and friction forces. So it is our starting point to improve, to generate a better aerodynamic analysis methods. So let's summarize everything here. Let's get started with the strengths of the method. Well, the first thing that we realize is that the origin of the forces is quite easy to interpret. We have realized that the pressures forces are driven by the CP distribution. The friction forces are linked to the velocity field around the body. So it's quite intuitive to understand the pressure and friction terms and ultimately the total drag. That's a very good point. Then the other advantage is that this method is quite easy to implement in CFD code, and in fact all the CFD solvers, the drag and lift values they shown each time you perform a CFD conversions are based on near-field method. Then another advantage is that the friction and pressure drag visualization is quite fast. Indeed, basically what you need is just the geometry of the surface. You don't really need volumetric information. Since you are dealing with the geometry of the surface, it means that the amount of data you are managing is quite small, so it's quite fast to implement the formulation. So the visualization and data treatment is quite fast. The other advantage of this method is that allows you to determine lift drag in a very fast manner. For both approaches, the total values of lift drag as well as the span-wise distributions. So as I mentioned before, near-field method is quite practical. It gives you a good starting point to perform further detailed and physical and meaningful analysis by other methods. But what are the drawbacks? Well, there are several drawbacks with this method. First of all is that this approach is quite prone to numerical errors. First of all, it requires a fine grid, especially around the leading edge, in order to avoid, the method is based on the force acting at each surface, and the surface element is defined by its normal. If you have a coarse refinement around the leading edge, you will somewhat averaged the force acting at each surface element, and you will start adding errors. So this is quite complicated. You really need to refine the leading edge, the trailing edge in order to get very, very good accurate results. The other problem with this method is that it is only suited for CFD, and let me show you why. Indeed, as I mentioned before, it requires pressure and friction forces acting upon the surface. These parameters are fully available from a CFD data. However, in a wind tunnel testing environment, you can measure the pressure distribution acting on the entire surface. That's doable. It's hard but doable. But the problem is that the wall shear stresses cannot be measured on the entire wind tunnel model. It's completely beyond the scope of the current state of the art. So basically, you cannot apply the entire equation of the near-field method because the shear stress term will be lacking. You can only compute the pressure forces. Another drawback of this approach is the limited of physical analysis. As I mentioned before, when we compare the 2D against the 3D characteristic curves, we realized that the three-dimensionality of the flow is not being put in evidence. It's basically 2D and 3D cases are providing very similar curves. The shape of the curves are quite similar despite the values. So this is not practical. I would really need to visualize only the 3D phenomena. And other problems that its breakdown do not highlight the sources of losses. We will understand that better once we advance with the other methods. Right now, what we can say based on the previous analysis is that we can just link, for example, the lift generation or lift distribution at a given point with the pressure distribution, and that's all. But if you want to go beyond and to understand what is generating a given source of drag at a given point, it's quite difficult to know what to modify. And this is better analyzed with other methods, and the other are more powerful for design purposes. As I mentioned before, the drag breakdown is only based on pressure and friction. There are better ways, so we'll realize very quickly that this drag breakdown is a very good starting point, but it's not quite practical for design purposes. So having said that about the near-field method, we will advance with the other methods. We will see an increasing level of difficulty in terms of equations, in terms of physical, but the reward of this difficulty is the level of physical understanding and its impact on the design. So let's tackle the widely used far-field method. Indeed, this is not just a method. There are plenty of far-field methods, and all of them are control volume based. So let's go for it. The very first far-field method is basically what we call in theory the momentum conservation equation, basically. So this is a control volume approach. Let's say, let's consider, for example, an aircraft, and let's consider a control volume surrounding this aircraft with our aerodynamic reference frames as defined before. The external control volume is defined by several surfaces: the upstream surface, the lateral surfaces, and the outlet surface. So the idea behind the momentum conservation method or momentum conservation equation is to apply the momentum conservation equation to the control volume surrounding the aircraft. And as you have seen in your aerodynamic theory, this equation, the momentum conservation equation, must be applied to all the surfaces of the control volume. That is, the external surfaces, upstream, lateral, and outlet, but also the surface acting upon the body. That is the internal surface of the control volume. And this surface, we will call it surface body. So what's the objective of the far-field method based on the momentum conservation equation? Well, the first approach is to apply the momentum conservation equation to the control volume and then to do some specific manipulations. The very first equation manipulation is to do that. Basically, is to split this integral to separate the part acting upon the body on one side and the part acting on the external surfaces of the control volume on the other side. So this is what you get. It's the same equation, just split, and that's all. And you will immediately recognize on the left-hand side that this is the near-field forces that we discussed before. So basically, this is the near-field method, mathematically linked to the control volume. We know this force. We can compute that by the near-field method. And the interesting thing about this is that the forces acting upon the body that are this equation can also be determined by doing an integral of the forces acting on the external surfaces. So this is the basically action-reaction by momentum conservation. And that's why this is called far-field forces, because we are predicting the force acting upon the body by measuring parameters on the external surfaces of the control volume that are far away from the body, and that's why we call it far-field forces. So the momentum conservation equation basically allows us to establish the force acting upon a body, basically that's the near field method, is given by this expression, this general expression, that's basically the momentum conservation equation applied to the external surfaces acting upon a body. The problem of the formulation as it is that it's not that practical for CFD applications. It's absolutely prohibitive for wind tunnel applications, and let me explain you why. For CFD applications, it means that if you want to compute the force acting upon a body, you have to define first a control volume around, and then to compute this parameter, velocity, density, and pressure, and so on, acting on each surface. That's doable, but it's not that practical because that implies defining the control volume, and the size of this control volume will depend on the shape of the geometry and so on. This, in any case, is a smaller drawback, but it becomes absolutely prohibitive for wind tunnel testing, and this is more evident. Why? Because in a wind tunnel testing, you cannot afford to measure all these parameters on all the surface. That will require a lot of time, a lot of wind tunnel testing time, and simply you cannot do that. What you would like to do in a wind tunnel testing environment is that instead of measuring parameters on all the surfaces of the control volume, you would like at least to measure parameters at the survey plane, and ideally just across the wake. We will see that later on. We will just do in the next section just a small improvement. That is, instead of performing this integral on the total external surfaces, we will just perform this calculation only on the outlet section. We will find a way to get rid of the forward external surfaces and the upstream external surfaces. So let's go for it. This method that I mentioned, it will be called single survey plane. How it works? Let's get started from the equation we derived in the previous slide, that is the force acting upon a body obtained by the far field method is simply the integral of the momentum conservation equation terms on the external surfaces of the control volume. But what we can do in order to get rid of the lateral and upstream phase? Well, there's a way to that. First of all, we will use this equation that's derived from the divergence theorem. This is just an identity that can be demonstrated. We will use another identity that's obtained based from the mass conservation. As you can see, the first term is related to the pressure and the second term is related to the velocity. And both the pressure and the velocity have the subscript 0. That means that these parameters are referred to the upstream value, the upstream reference value, whereas these values, B and PS, are local values at the surfaces of the control volume. And why I'm introducing these two equations? Simply because I will combine these three equations together and obtain this. Basically, what I'm doing is manipulating the equation in such a way that instead of having the velocity here, the fact of introducing this equation allows me to re-express the velocity in terms of the change of velocity. So the velocity now is referred to the changes respect to the upstream value. And in the same manner, previously we have just the static pressure at each surface. Now, by introducing this equation here, we can change that, and instead of talking to the local static pressure, we can now talk about the changes of static pressure at each point lying at the external surfaces of the control volume. What's the interest of doing that? What's the interest of converting this equation into this equation? Well, the advantage is that the fact of using perturbations, because this is a perturbation of velocity, perturbation and pressure, will allow me to get rid of the lateral and the upstream surface. Just in order to achieve that, let's assume that the control volume, or the surfaces of the control volume, are placed far away from the body. That is, the upstream surface A0 is pushed far upstream, and the lateral surface I pushed away and they go to the infinite. So in those surfaces, S0 and the lateral surfaces, they are so far away from the body that there are no flow perturbations at those surfaces. The velocity perturbation will be 0 at those surfaces, and also the pressure perturbations. So basically this term will be 0 and this term will be 0 in those surfaces. So the integral does no longer require to be computed on these surfaces. I can just compute that on the outlet surface. And that's the idea. Basically, by introducing this equation, I obtain this expression here that remains exact. It has the same degree of validity than this. The only assumption that we are introducing with this method, the single survey plane, is that we are considering that the control volume surfaces are far away from the body, except the outlet surface that's close to the body. And then by doing so, I can compute the forces acting upon the body only by integrating this momentum conservation equation, or variation of the momentum conservation equation, on the outlet surface uniquely. The only thing that you have to take into account is that now this outlet surface has an infinite size. Why? Because we have pushed the lateral surface far away, so the outlet surface will have an infinite size. This is the basis of the single survey plane. That's a sub-method of the momentum conservation equation. Now, let me show you an application of this survey plane based approach. Basically, since the equation can now be applied at the outlet surface, I can put the survey plane anywhere around the body. So this is the case. Let's consider, for example, a 2D case and the flow field around it. In black, you have the survey plane that's normal to the upstream flow direction. That's the standard practice. And along this plane, I can compute point by point both terms of the modified momentum conservation equation. That is the velocity term and the pressure term, point by point. Because at each point, I know the velocity, I know the pressure. So, since I know these parameters, I can visualize its related distributions, the distribution of the pressure term and the distribution of the velocity term. By combining both terms, I will obtain the total drag distribution all along the survey line. So before tackling the particularities of all this, basically the major objective of applying this formulation point by point all along the survey line is that this will allow me to determine the local drag density at each point, and ultimately, by integrating data on this infinite plane, it will allow me to determine the total drag. That's the major objective of this method, to compute total drag based only the information available at this black survey plane. That's all. Now, let's tackle the particularities of this method. The first thing that we realize when we observe its components, the pressure term and the velocity term, is that we can see there's a sort of coupling between the pressure and velocity. We can realize that where the velocity varies, also pressure varies. So there's a sort of coupling between those terms. And as you can see, for example, here, you have a positive velocity term and also you have a negative pressure term, so it's difficult to say here what's the meaning of each one of the terms, knowing that the local drag at that point is 0. So this starts being difficult to start analyzing each one of the components of the term. Then the other thing that we have to take a look is that inside the wake is the part marked here in red. The black survey plane slices the wake at this region, and across this region you can see that the blue curve corresponding to the velocity term has a peak inside, and this is related to the loss of momentum across the boundary layer or across the wake. As you can see, this affects only the velocity term, but not the pressure term. The pressure term is unaffected by this velocity defect inside the wake. And that's why, as you can see, drag has a peak there related also to the velocity deficit. So as you can see, this peak is mounted on the top of a baseline distribution that continues here, somewhat here. So we can realize that there are two physics overlapped. Baseline physics that continues here, here straight, and another part of the physics that's related to the peak here. And also we can realize that the baseline physics that continues here is related to the pressure. So we can start realizing the links between pressure, velocity, but velocity is far more complex, contains another effect. So this is powerful in the sense that we can start interpreting the meaning of the flow parameters, but it's not yet well prepared in the sense that it requires a lot of analysis to try to figure out what's happening, and it is just a 2D case. A 3D case is far more complex. Another problem that we realize of this distribution of drag along the black survey plane is that drag is not zero outside the wake, and based on our knowledge of physics, we know that for a subsonic case, drag only is related to the loss of momentum inside the boundary layer. We don't expect having a positive drag value. And if you take a look here in the detail, you will see here that there is a negative drag value. So what's that? Why we have a positive drag here, negative drag? What's the meaning of that? Well, we start seeing that we don't have yet the answer for that. We'll have that afterwards. But what we can say here is that there's the physics is quite complex, and the formulation only is intended to provide the total integral of this distribution along the survey plane, and we're providing just a single value, drag. That's all. It's not intended to be analyzed point by point, because when you do that, you will start finding some not inconsistencies, but some hard points that are difficult to explain with this current theory. It will be better explained with advanced theory that we will see afterwards. And another problem that I highlighted before that can be better seen here, if you plot the drag density not only at each point of this line but at all the points of the entire field, you will better visualize that there are zones with positive and negative local drag. So again, what's the meaning of that? Why we have drag and thrust here? What's that? Well, we will better understand that if we keep digging in the formulation and we obtain advanced formulations. So let's summarize what we have been discussing about this momentum conservation method. That's the very first far field method. First of all, it's concerning its strengths. This is quite easy to implement in CFD codes, simply because you just need to launch your calculations and you just need to slice the domain downstream of the body, and the data available at the survey plane, you just need pressure, velocity, density, and that's all. With that information, you are able to compute drag by integrating data on that infinite surface plane. Then we will provide you a fast physical analysis. Well, it's not that detailed as I mentioned before. There have some drawbacks, but at least you can start figuring out what's happening from a physics point of view. That's good as an entry level. We'll go that further beyond with other methods. But the very interesting point of the momentum conservation method is that you can compute drag very fast and very accurate only based on data available at the survey plane just downstream of the body, and that's the major application for CFD to compute total drag in an accurate manner. And this is even more accurate than near field method, provided the mesh refinement is good enough across the wake. But what about the weaknesses? Well, first of all, this method is only suited for CFD. Why? Because in CFD you have everything you need. You have access to the infinite survey plane, you have access to velocity and pressure and everything you need. However, if you want to measure these parameters on the entire wind tunnel cross-section, you can do that, but that will take a lot of time and it's not practical. So this method, as it is, cannot be applied yet to a wind tunnel testing. The other problem that I highlighted before is its limited physical analysis. Indeed, you can analyze the flow physics, but you will realize very rapidly that there are some weird things out there that are quite difficult to interpret, to analyze. So you start realizing the limitations of the theory itself. The other problem is that its breakdown, I mean the pressure term and the velocity term, do not really highlight the sources of losses. There are a lot of physical levels mixed in those terms, as we discovered that before. So we need to find a way to keep decomposing each one of the terms to really separate all the physical layers that are at this point mixed together. So at this point, the drag breakdown proposed by the current momentum conservation method is not useful for design purposes. And that's why we will improve that with the weight-reduced method. The idea behind the weight-reduced method is the following. Just a quick reminder, we have started first with the momentum conservation method that was applied to all the surfaces surrounding the control volume. Then we have improved that and we just have performed or computed drag based only the outlet plane. And now we will do a step forward and we will only compute drag by taking into consideration data only inside the wake. And that's a major achievement because this will allow us to implement the equation for wind tunnel testing. But not only that, it will also give us a lot of physical understanding of what's going on, and we will find out that the resulting formulation is extremely useful for design purposes. So let's go for it. Let's find how works the weight-reduced methods. So there is not just one method. Indeed, there are plenty of methods, and this list is not comprehensive. I just gathered here the most represented methods. As you can see, the history is quite old. It started almost 100 years ago with Betz. In 1925, he developed the very first weight-reduced method. We will talk about that in just a moment. But after that, there were plenty of researchers that were improving the formulation in order to tackle some limitations or drawbacks that appear on the existing state-of-the-art. And currently, the most advanced formulation that you will find out in this method is quite robust. It's the one I used each time I want to perform aerodynamic analysis. It's quite accurate. It was developed by Onera in France in 2006. So it's one of the reasons. There are other out there, but this is really quite robust. So how what's the procedure we have to cross in order to arrive to this level of maturity? Well, it wasn't easy. As you can see, or as you have discovered in our previous analysis, the physics analysis or the flow physics analysis is quite difficult. It's quite complex, especially when you have 3D flow physics involved. When you have shock waves, it starts becoming more and more complex. So all these researchers were added at each their time layer of evolution. So we will deal with some few of them in this presentation. Betz, it will introduce just in the next slide because this was the first one and because this has settled the base of how it works. Then, but the problem of the Betz method, it was only for 2D cases. That's why later on Maskell established a major milestone by extending this formulation to 3D bodies. We'll see that formulation in detail as well. But up to this point, up to Hackett, it was only incompressible flow field. So then it was Van der Boren, afterward Kusunose, that it improved the formulation to take into account compressibility, and then Kusunose also was the very first to identify the weight drag extraction. So all these milestones will be presented in the next sections. Things first things. So before tackling the wake-reduced formulation, I will present what is called the velocity decomposition, because this is the core of the wake-reduced formulation. What is this? Well, let's consider the actual velocity field of a given airfoil. This is an actual airfoil in a subsonic case. You can actually see the stagnation point, acceleration around the body, and even you can see the wake here in this region. And let's take a survey plane very close to the body, is this cyan line here. And all along this line, I will plot several distributions. This is the survey plane that I mentioned before, and this is the actual velocity profile. And as you can see, we get the typical velocity profile. You have an external velocity field with a given magnitude, and then you start having this wake velocity deficit all across the wake. That's related to the loss of momentum inside the boundary layer, so this will be somehow related to drag. And then the velocity field continues having what is called isentropic evolution. That means that the formation of the velocity field is related to the presence of the body, but it's not related to the viscosity effect itself. This is related to the viscosity. So the idea behind the velocity decomposition is to break down this velocity profile in two components. A first component here in blue that gives me the baseline velocity profile if no losses were generated, and this is called isentropic velocity and is symbolized with U star parameter. Basically, this gives you the velocity distribution without taking into account the losses due to the boundary layer, for example, the viscous losses. So since there are theoretically no losses, this peak here will no longer exist, and the velocity distribution will just keep crossing across the wake as if nothing would happen. And the remaining part of the difference between this white and blue curve is this one. Is the basically will give you the velocity deficit inside or across the wake. You can see it's 0 outside the wake, and then you have a negative velocity value across the wake that's related to the loss of momentum across the wake. And this is symbolized by the U bar and is known today as a non-isentropic velocity component. We will talk about that afterwards. But now we just keep in mind that the idea of the velocity decomposition is just to decompose the total velocity field U into two components: the isentropic velocity component U star and the non-isentropic velocity component U bar. This ignores any effect related to the viscosity, and this only includes the effects of velocity, the viscosity, that is the velocity deficit across the wake. So let's see how it looks like for entire velocity field decomposition. What we are seeing here is the actual flow field of the actual velocity in this case, where again we can see the isentropic field around the airfoil and then the viscous effect in the boundary layer and the wake. And then, based on the idea of the velocity decomposition, we can decompose that in two components. The first component is the isentropic part, and as you can see, we have taken away the effect of the boundary layer and the wake. You can see that it is no longer existent. We're just retaining the part of the flow field related only to the perturbations of the body itself, but not the effects of the viscosity. Where are the effects of the viscosity? In the other components. This component is the isentropic part, the other component is the non-isentropic part. As you can see, this time, this component, the non-isentropic part, will only contain the effect of the boundary layer and the wake. And outside, it will be 0 everywhere. 0 is red is 0 here, so we can see that the field is actually 0 outside and negative inside the boundary layer and the wake. It is negative because it is related to the velocity deficit, to the loss of momentum across the boundary layer or across the wake. So the interest of doing such a decomposition is that it allows us to dig more into the physics to understand what are the different sources that generates drag. So in this case, we can realize that the physics can be simplified into two terms. A term that here is called isentropic part, that basically, since there are no losses, we can say that for a subsonic case, this is equivalent to a potential flow field. And in potential flow field there is no drag, so the isentropic part will generate no drag, and whereas the non-isentropic part is related to the loss of momentum inside the boundary layer, so it's related to the drag generation. So the idea behind the velocity decomposition is to decompose the entire field to separate the part that do not generate drag from the part that actually generates drag. And this is a major step towards our physical understanding and to develop a more powerful far field method. And this is the concept behind the Maskell method. So as I mentioned, this is equivalent to potential flow field and it's not related to drag. This is the major concept you have to retain of the isentropic part. And for the non-isentropic part, this is related to the viscosity and it's weight reduced. So keep in mind that, because we will use that in the next section. So let's go back to the Betz method. Betz basically was the very first person to realize of this velocity decomposition, and he proposed the following. So let's consider an airfoil. In blue we have the limit of the viscous region, in black we have the sorbet plane, and all along the sorbet plane we have in blue the actual velocity distribution. That's the real velocity distribution that you will measure in reality or if you compute in CFD. So the idea behind the Betz method is that he wants to compute the U star value, that is the isentropic velocity, that is the distribution of velocity if no losses were involved. How he managed to compute that? Well, he proposed this expression that was obtained from the Bernoulli equation. If you remember, Bernoulli equation considers an isentropic flow where no losses are involved. So he's able to compute the isentropic velocity here based on the total pressure deficit at the sorbet plane, at each point at the sorbet plane. So this was the very first expression allowing us to compute the isentropic velocity. And then it was a major breakthrough because we can now perform the velocity decomposition. So what proposed Betz is to implement this velocity decomposition into the momentum equation that we have developed before, that is the single sorbet plane version of the momentum conservation equation that requires a sorbet plane downstream of the body and the sorbet plane is of infinite size. Well, by putting this equation here and doing some extra manipulation, we can obtain this expression that's known today as the Betz method. And basically, of course, you take only the x component of this expression because we are interested in drag. The drag known as profile drag, I will go back about this in just in a while, but basically drag is given by this expression that, as you can see, it contains the total pressure deficit that comes from this term here, and also you have a difference between the isentropic velocity and the real velocity. The isentropic velocity comes from here. So basically, as you can see, this equation has been included and manipulated, and we start having a more physical understanding of drag, because drag is now related to the loss of total pressure, and you know total pressure is a measure of the energy of the flow. If you lose energy due to the viscosity, you will generate a total pressure deficit, and that's drag. But you also have a velocity deficit. The difference between U star and U basically is this distance here, is the velocity deficit across the wake, is this part here. So this term is basically the velocity deficit, so it also generates drag. There are two sources of drag: the total pressure that you lost inside the boundary layer, but also the velocity deficit that remains across the wake at the sorbet plane position. So as you can see, the Betz method allows us to take away the part that annoys in the analysis, that is this isentropic field, and only retains the really sources of loss of energy, the really sources of drag that are the loss of total pressure and loss of kinetic energy. And even more, the advantage of using this decomposition is that you will reduce this integral that before it required an infinite solid plane. Now it just requires an integral across the wake. Why? Simply because this term and this term will fade out, will be zero outside the wake. Indeed, outside the wake, there is no total pressure deficit, so this term will be zero. And the outside the wake, U star and U are identical, so this term also will be zero outside the wake. So as you can see, this integral is only non-zero inside the wake, and that's why we can compute drag only inside the wake by measuring total pressure loss and some kinetic energy parameters. Then, why it is called profile drag and not simply drag? Well, because this expression here is only valid for 2D cases. He has consider a non-lifting body. He has assumed that the airfoil that he's studying is actually not generating lift, so it's just a drag generating element. This drag is just associated to the shape of the body itself, that is to its profile, and that's why this is called profile drag. It's just a drag only associated to the shape itself, but it's not related to the lift. So this is expression that we developed before. This is the profile drag, and as I said before, is the weight integral of the total pressure deficit and the kinetic energy associated to the velocity deficit. So we have this total pressure deficit term here, and that, as you know, is related to the loss of pressure energy inside the boundary layer. And this term here is basically the velocity deficit, so you have a drag associated to this loss of kinetic energy. And again, I stress the fact that this formulation starts delivering a more physics-based analysis, and it's easier to interpret the sources of drag by just analyzing the terms. And this wasn't the case with the near field or the previous far field method. So this was really a major breakthrough, a major milestone in the history of the aerodynamic analysis methods. So let's summarize all what we discussed about the Betz method. Regarding the strengths, we have, by the very first time, a weight-reduced formulation, and the advantage of having a weight-reduced formulation is that we can apply that for CFD, but finally for wind tunnel testing. So since 1925, we were able to measure profile drag in a wind tunnel environment. It wasn't possible before that. So that was a major achievement for Betz. And the other advantage is that you can determine profile drag very rapidly. You just have to measure total pressure and velocity behind the wake of the airfoil, and that's all. So it's quite easy to determine that in wind tunnel, and of course in CFD is even easier. And the other advantage is that the source of losses are well identified. As I mentioned here, the physics lying behind the drag generation is explicit, it's clear, it's crystal clear right now. This allows us to perform a fast physical analysis independently of the complexity of the case that you are analyzing. So this formulation, the Betz method, has settled the very first milestone. Of course, this can be improved, and we will see later on how we can improve. And why we have to improve that? Well, because the formulation is not perfect, there are some defects. The very first problem is that this equation is only valid for non-lifting bodies. As I mentioned before, the expression that Betz used for the isentropic velocity has assumed that the body itself is not generating lift. It's just a profile drag generating body. So we have to find a way to take into account the lift generation, and this we will tackle in the next slide. And the other problem is that the equation Betz used for the isentropic velocity is based on the Bernoulli equation, and the Bernoulli equation assumes incompressible flow. So you cannot apply this equation for compressible flow fields. So this is a limitation, and that will be tackled afterwards. So let's go for it. Let's tackle first the problem related to the 3D cases. So I'll go back to the schema that I showed you for beds, and this time Muscle realized that the equation that beds proposed is okay, will be fine even for a 3D case, as long as you include, besides the isentropic U component, if you include the transverse velocity components B and W, you will have realistic value of the isentropic velocity. So the procedure is quite similar. The only thing that has changed is that this time he includes the B and W velocity components. That is the transverse velocity components. That's the only difference with beds. So again, you take this equation, you take the momentum conservation equation along the x-axis, you mix that together, and you get this expression here, known today as the Muscle method. And as you can see, it's quite similar to the beds method. You will realize this term related to total pressure, and this term to the kinetic energy deficit across the wake. These two terms are the beds equation that we have discussed before, but now there is a new term here related to the transverse velocity components, B and W. This is the transverse kinetic energy in reality. You have half B squared. And the other problem that you will realize is that at this point the integral cannot be reduced to the wake, and let me explain you why. Well, first of all, this term here is a term called isentropic velocity perturbation. It's basically the isentropic velocity field referred to the upstream velocity. Basically, this is U star, the isentropic velocity. So this term is basically the perturbations of velocity respect to the upstream reference value. So in this case will be all negative of a small quantity. So having said that, let's tackle this equation in detail. First of all, as I mentioned before, we can decompose it in two parts. The first part that takes into account only the pressure and kinetic energy deficit, as before, and this will give me the profile drag. That's the beds method, and this is wake reduced as before. So the first part of the equation is known because this is beds. The newer part is this one related to the transfer kinetic energy, and this is called the vortex drag. And this requires integrating the transfer kinetic energy in an infinite survey plane that's placed behind the body. Notice that this is wake reduced and this is not yet wake reduced. It requires measuring parameters on an infinite surface, and this is a problem because for our practical applications I will really need to measure or find a way to compute this only reduced to the wake. So the left hand side basically is bed and it's reduced to the wake, and on the right hand side we have to compute the rotational or transfer kinetic energy on an infinite a plane of an infinite size, which is not reduced to the wake. So we'll tackle this problem first. How can we achieve this wake reduction? Well, Muscle realized that the vortex drag associated to the rotational flow field generated by the vortices, for example, can be mathematically identical to this expression here, where you have a stream function and the axial vorticity. And since the axial vorticity is related only to the wake, is only contained inside the wake, this expression allows you to compute vortex drag only from wake data. But what's the meaning of these terms here? What does it mean? Well, this term is the axial vorticity. It's basically the rotational of the flow field along the aerodynamic x-axis. This is related to the lift generation, or basically in a lifting line environment, it's basically the filaments shed by the wing lifting line. So the same vortices that have generated lift are shed downstream and generate vortex drag. So it's clear this expression if you do the link with a lifting line. And the other term here, the stream function, is a Poisson equation that is driven by the axial vorticity itself. Basically, this is the stream function associated to the rotational flow field around the vortices. We will understand that better afterwards. For the time being, just be conscious that the stream function is just the function that is driven by the axial vorticity. So basically, this is vorticity, and vortice is only a parameter reduced to the wake, so you can compute vortex drag related to the vorticity, which is a measure of the vortex. So basically, when you see this with this, it's the same thing viewed from another point of view. We will understand that better in detail when I present you the Epsilon module that explains how to compute vortex drag. So for the timing, just to retain the basic equation, but don't be a problem about the physical meaning. Just to better understand what's that, so let's consider a wing, and with this image I will try to explain what we have done. Basically, if you have the wing and you take one of the cross section of the wake, let's take for example this one. At this section, you have at each point of the cross section, you have the total pressure deficit. You can compute the axial kinetic deficit. So basically, you can compute the profile drag at this wake section. But if we go to the other term, this term here is the vortex drag, and basically it requires computing the transverse kinetic energy in an infinite survey plane. Let's suppose that this is the infinite survey plane. At a given point, I have the transverse velocity components. So what it requires, these terms, is basically to integrate this transverse kinetic energy at each point all along the survey plane. So basically, it's the amount of energy you spend to make the flow to rotate by the vortices. And the alternative expression says that an alternative way to compute this rotational kinetic energy is to basically integrate vorticity in wake by using this Poisson equation. Indeed, if you at that plane you compute the vorticity at the wake and use this vorticity to solve this Poisson equation, you will obtain the stream function C here that will give you constant lines around the vortices, and actually each line of constant value is basically the streamline at the survey plane. You can see that the particle is actually rotating around the vortex induced by the velocity induced by the vorticity itself. So that's the meaning of the stream function, and then by doing the product of the stream function and the local vorticity will give you the vortex drag. So that was all regarding drag, but Maskell went beyond and also analyzed lift. Basically, he was inspired on the lifting line theory. Basically, the lifting line relation says that the changes in circulation along the bound vortex is related to the actual vorticity shed by the filaments. So he used this lifting line relation. He introduced that into the momentum conservation equation along the z-axis, because we're interested in lift right now. If you combine this equation with this relation here, and after a lot of manipulation, you can obtain this expression that's known today as the Maskell lift expression, that is given by two terms. The term on the right hand side is negligible. You can ignore that. It's just related to the downward velocity W. So it's a small downwash correction, but it's really absolutely negligible. So basically, in practice, lift is only given by this term. And as you can see, this term, you have two particular parameters. The lateral position of the vorticity, see that here. So its product will generate lift, and we will understand that better in the next slide. So this is the approximative or simplified lift expression for Muscle. That, as I mentioned before, is basically the product of the vorticity and its lateral coordinate along the span. Of course, you have to multiply that by density and velocity, just constant values. And since vorticity is a wake radius parameter, you can integrate that only across the wake. So how it works, how this help me to understand the physics, how it will help me to do a design. Well, let's consider this wing here. This is the wing, the view from the front or from the end. Basically, what we have is the tip vortex here. We have another tip vortex at the end of the flap, another tip vortex at the end of the inner flap, and a counter-rotative vortex at the end of the inner board flap. And having that in mind, if we perform a wake measurement, we will get something like this. This is the actual measurement of the wake, the vorticity at the wake of this particular wing. We can identify here the four vortices. We have the vortex at the tip of the wing, the vortex at the tip of the outer flap, the vortex at the tip of the inner flap, and the inner vortex. And as shown here in red and in green, these are counter-rotative vortices. And the flow in between is pushed downwards, whereas the flow outside tends to go upwards. It's better, it's clear here, it's going upwards. So how can I use the Muscle expression to analyze this? Well, just keep in mind that a red arrow like this is rotating in this way, and this corresponds to a negative vorticity. If this green is rotating in this direction, this is a positive vorticity. And also keep in mind that this has been measured on the left-hand side of the wing, where the coordinates, span-wise coordinates, are negative. So this will give me basically the lateral coordinate of a given vortex, and I have measured the vorticity at each one of the vortex. So basically I can compute the contribution of each one of these vortices to the lift, and based on that to reconstruct lift based only on the vorticity field. Let's go for it. What I got here is the same wing and the measured lift distributions along the span for different angles of attack. And you can easily understand why the lift distribution has this particular shape based on this vorticity measurement and this expression. And let me explain you how to understand that. First of all, here at the vortex, the tip, we have a vortex that is negative and its coordinate is negative. So the product of the coordinate and its vorticity will be positive, and this will generate an increase of lift at the position of the vortex. The same will happen at this vortex here, where an increase of lift due to the vortex here, and also here, where its product of the coordinate and the vorticity will produce an increase in lift. But here we have a positive vorticity and a negative coordinate, so it will generate a negative contribution to the lift, and that's why here it's reduced. So basically you can have an idea of how will look the shape of the lift distribution only by taking a look at the vorticity distribution if you have in mind this Muscle expression. So that's the powerful behind the Muscle expression. It really allows you to understand the implications of the vorticity, and you know vorticity is generated by the surface, so you can actually link the geometrical parameters with the vorticity generated, with the lift it generates, and also with drag, because don't forget that drag, vortex drag, can be computed only from actual vorticity. So the key parameter here is actual vorticity, and it's linked with the geometry. So what's the physics behind this simplified lift expression for Muscle? Well, it can be better understood based on the vertical impulse. Let's consider two counter-rotative vortices. These two vortices will induce a rotational flow field in this case is counterclockwise, in this case is clockwise, and in between there will be a downward velocity. And in particular, if you integrate the entire flow field, you will have a downward net momentum. And this is given, the net momentum is given by the magnitude of the circulation of each vortex and the distance that separates the vortices. And if you take a look at this, basically it's the same thing. Instead of talking the circulation or the magnitude of the vorticity, we are talking about the product of the vorticity times the surface. The product of vorticity and the local surface will give me the circulation. And this is a distance between vortices, that's the coordinate. So this is the theory behind this expression. So this allows us to bring the theory to a more familiar ground. And we can even go far beyond. This is the expression that relates the circulation with the vorticity. You know that circulation is the dot product of velocity along a closed curve, or the flux of vorticity. So you need the vorticity and the surface, that's this product here, that gives you the circulation, that's this term here, and then you have gamma, that's the term here. So basically, when you have two counter-rotated vortices, you will have a net downwards impulse, and this will generate lift by reaction. So that explains why this expression gives you lift based only on vorticity. It's not just vorticity, it's the circulation associated to this vorticity and the separation between vortices. And you can better observe that here, this experimental data you can find in the website. You can actually see the two vortices generated at the tip, and there is a net downwards momentum that's generated by these two counter-rotated vortices, and this momentum by reaction gives you lift. So that's the physics behind the Muskel lift expression. Now let's bring this to a more practical region. Let's consider the case of CFD data for rectangular wing. Let's say that I can get the wake data at a given survey plane position, and at that plane I have everything. I have the total pressure deficit, I have the actual kinetic deficit across the wake, I have the actual vorticity, so I have everything to compute the far field method based on the Muskel approach. What's that? Well, first of all, it allows me to compute a profile drag shown here in cyan. That's the distribution of profile drag all along the span. You can actually see that here's almost a constant value all along the span, and then here you have a peak of profile drag that's related to the energy lost inside the vortex core. And then you have vortex drag. Vortex drag, as I mentioned before, is related to the actual vorticity, and as you can see, it's almost zero along the span. It's mostly concentrated at the tip region where you have the vortex indeed. And also, based on vorticity, you can integrate that and compute lift distribution as shown here. So as you can see here, this lift distribution is quite similar to the lift distribution we obtained before by the near field method. The advantage is that this time we have obtained that only based on wake data, only using vorticity. And that's the power behind the Muskel method. We can now start digging into the physics to better understanding what are the real parameters that drive drag generation, drive lift. With the other methods, with far field with the near field method and the momentum conservation equation, it wasn't that straightforward. Now with BETS and Muskel, we can really start understanding how it really works, the physics, how drag is generated, how lift is generated. So we can use the Muskel method to establish the characteristic curves as we did before for the near field method. So let's take again our airfoil, our NACA12 airfoil, and we will do a sweep in angle of attack, and we will compute drag, this time by near field, far field method. That's all. In 2D cases, there is no possible to do a breakdown with the far field method, whereas if you remember, near field method allowed me to decompose total drag into pressure and friction drag. with far field method, you can eventually use the components, but this is not that practical, so we'll just stick to this. Regarding the 3D cases, this time total drag can be computed by far field method and decomposed into this viscous and vortex components. And as you can see, this viscous component will be related to this curve here, whereas the vortex is only a 3D phenomenon, something that doesn't appear in 2D cases. So now we have a more realistic representation of the physics. In 2D cases, I only have the profile drag, this curve right here. But in 3D cases, besides profile drag, I have the 3D effects that is linked to the vortex drag. And of course, the addition of these two phenomena will give me the total drag. And as you can realize, this overcomes the problem that we had before with the near field method. With near field method, we were able to decompose drag, but the decomposition was identical for 2D cases and 3D cases, which was not so physical. In this case, we have something that really changes from 2D to 3D. It's crystal clear what's new in 3D phenomena. So let's summarize all that. We'll start first with the strength of the Maskell method. The very good news here is that it is a weight-reduced approach, so we can use that either for CFD and wind tunnel testing methods. Both Maskell and Betz are available in Epsilon. You can compute drag lift based on CFD and wind tunnel data. Then the other strength of this method is that the source of losses are well identified. Now we can relate drag to the total pressure deficit, to the kinetic edge energy deficit inside the wake, to the axial vorticity shed inside the wake. So these are three different physical mechanisms that generate drag. The first two, the total pressure deficit and the kinetic energy deficit, are related to profile drag, whereas the axial vorticity, related to the rotational kinetic and edge energy, is related to vortex drag. So now it's crystal clear the physics. And that gives us our new decomposition into vortex drag and profile drag. But what's the problem of the current formulation for Maskell? Well, the only problem so far is that it assumes incompressible flow simply because he still uses the Bernoulli equation. So that's the only problem that we have to overcome. Let's go for it. In order to overcome this problem, a completely different approach was developed by van der Boren and afterwards refined by Kusunose. That's known today as a small perturbation approach. This is a subcategory inside the far field methods. So basically, what's the idea? You will start, of course, from the momentum conservation method, because this is the mother equation in the far field method. And the only thing that you will add on the top of that is that this time you will introduce perturbations to each one of the parameters. For example, velocity, density, pressure. You will introduce parameters, or will represent that as a upstream volume plus a perturbation generated by the body. And then by introducing these perturbations and by doing a lot of mathematical manipulation, you can obtain expressions of this kind. This is, for example, the one developed by Kusunose, where drag is basically, as you can see, a bunch of terms where you have perturbation of entropy, perturbation of enthalpy, and so on. So basically, the idea of introducing these perturbations is that allows you to avoid using the Bernoulli equation in order to manipulate all these expressions, and you have something that is weight reduced, as you can see here. All these parameters, entropy generation, enthalpy, and so on, are weight reduced, so you can actually compute drag based on weight data by following a completely different approach. This is mathematically more complex. It's more difficult to give a given physical interpretation to all these terms. We'll indeed understand better that afterwards. For example, here we can see that there is entropy. we'll realize later on when we talk about the exergy method that this is the energy, and this is related to the total pressure deficit. It's roughly equivalent to that. So you have here enthalpy, and the enthalpy is roughly related to the kinetic energy perturbation inside the boundary layer. So this is related to the vortex drag, to the actual kinetic deficit, so to the profile drag. And there are other mathematical terms of second order. You have entropy square and so on. So as you can see, by introducing the perturbations, you have other terms of higher order. Some of them has been ignored in this simplified expression, but you see in the first order you have roughly the same physics. You have the entropy associated to the total pressure deficit and the enthalpy variation associated to the loss of momentum inside the wake. So that allows you to obtain profile drag in a compressible flow field, because simply you are not using Bernoulli anymore. Well, Kusunose went beyond. He even developed a method to extract wake drag from profile drag. So let's consider this time a transonic case. We have a 2D airfoil, negative airfoil under transonic conditions. We have in red the boundary layer and the viscous part of the wake. And in green, we have here the shock wave and its related wake propagated downstream that belongs also into the wake. And let's consider this time a survey plane here in yellow. And all along this survey plane, we have the distribution of local drag density based on this previous equation. That's basically profile drag point by point. So, as you can see, this profile, if you integrate this profile, you will obtain the profile drag. That's all. That's what the methodology will allow me to compute. But Kusunose wanted to decompose this profile in order to separate the green part from the red part, that is the pure wave from the pure viscous phenomena. So he achieved that by introducing the following concept. He realized that the vorticity is only limited to the wake. So he realized that he can use this parameter to clip away this distribution in white, that is this one, depending on the part of the distribution that lies inside or outside the wake. So basically this is just a wake detection parameter. So the idea is the following. Let's say in red, this red distribution corresponds to this distribution. He said that everything that lies inside the red part will only be attributed to the viscous effect. So basically this peak here in red is attributed to the pure viscous effect, and this is shown here in blue. And the other part, if is attributed, for example, this part, what lies outside the wake, is attributed purely to the wake. It's purely to the shock wave, sorry. So that's the idea behind the Kusunose method. It's more a qualitative method that tags the cells that are inside or outside the wake, that basically split this distribution into two parts, the part inside the viscous region and the part outside the viscous region. So that's all regarding the far field method. We have started from the very simple method of beds. We have improved that to the Kusunose method, and we have something that's physically very meaningfully, and this is the state of the art. The perturbation methods are the state of the art, are quite accurate and quite representative from a physics point of view. But there is another method completely different that's called lamp vector, that allows you to perform also an aerodynamic analysis, but this time is fully based on vorticity. This is a completely different approach. Let's go for it. So we'll start from the generalized Kuta-Joukowski law. Basically, a small reminder: if you have a circulation gamma associated to an airfoil moving at the velocity v, it will generate a lift given by this product. So you can extend that and saying that if the same circulation generates this time is related to a downwash, the product of gamma and downwash will generate a drag. That's the vortex drag, and that's the typical theoretical things that we see in theory in aerodynamics. And we will extend that. We will, instead of talking of circulation, we'll talk about the integral of the vorticity. That's the flux of vorticity into 2D plane. The idea of digging a little bit more into detail, instead of talking the circulation, that's a more global parameter, we will talk about the vorticity as a more local parameter. The idea of doing that is that if we generalize this expression, we can say that lift is basically the cross product between velocity and vorticity. Again, vorticity times surface gives you the circulation, and velocity is here, density here. So as you can see, this expression is basically the Kuta-Zhukovsky generalized, and it requires integrating this quantity known as lambda vector, and that's why this method is called lambda vector method, because you have the cross product between velocity and vorticity, which is integrated across the wake. You know, vorticity is only a wake reduced parameter, so this integral only across the wake. And as we will see in the next slide, the lambda vector basically explains everything from a physics point of view. Let's go for it. First of all, as I mentioned, vorticity is a wake reduced parameter because vorticity is only inside the viscous region, inside the boundary layer or inside the wake. So based on that idea, let's consider, for example, the upper surface of an airfoil. At a given point, you have a certain amount of vorticity, shown here with this arrow, and also represented by this arrow here. That's the vorticity component along the span. And this is the velocity at which this vortex filament is advancing inside the boundary layer. So the cross product between this velocity and this local vorticity will give me locally a certain lambda vector component. This lambda vector along the z axis will give me lift. So again, lambda vector is cross product of velocity and vorticity locally, point by point. And if I take the vertical component of lambda vector and I integrate that on the volume of the boundary layer and the wake, I will obtain lift. This is another expression equivalent to the generalized Kuta-Zhukovsky. In the same manner, if I take the x component, I will obtain the vortex drag associated to the lambda vector. And as you can see, these are volume integrals of the lambda vector quantity inside the boundary layer and inside the wake. And profile drag is a bit more complex. You have this expression where you have other terms like spatial position vector, you have some normal to the survey plane, you have to define a survey plane downstream of the body, then you compute the normal of that survey plane normal, then you have some multiple cross products. It's mathematically more complex, but at the end of the day, this profile drag is just related to the velocity deficit. Just let me explain that better. Let's consider a body. Let's consider the velocity deficit across the wake. Basically, what this expression is saying is that there's, you have a lambda vector here. Lambda vector at the survey plane will be related to the vorticity along the y-axis here, shown with the arrows here in red. And this transfer vorticity, if we see that in the plane xz, you can model this velocity deficit as if we have just two lumped vortices here. We can lump all the vorticity distribution here into a single vortex here, and we can lump all this vorticity here into a single vortex there, which are counter-rotative as indicated here. And as we saw before, when we have two counter-rotating vortices, it generates an impulse in the direction of the vortices, and as a reaction we have a drag force. So we have an impulse to the left, the reaction is the drag force to the right, that is dragging the body to the right. So this is drag related do the transverse vorticity that is basic this expression here. So again, lambda vector contains all the physics. It explains lift, it explains vortex drag, and it also explains profile drag. And again, it is intimately related to vorticity. If you go back to the far field methods, you realize that Maskell also explained vortex drag based on vorticity, and also explained lift based on vorticity. But the far field method didn't relate profile drag to vorticity. Now it's clear that the velocity, that the impulse linked to the velocity deficit also generates profile drag. So we can profit from different aerodynamic analysis methods to improve our understanding of the physics. Of course, understanding such a mathematical complexity is not that straightforward. It requires reading and processing information a little bit, but once you manage to understand this method, lambda vector, you will have the missing key to attack any problem with the three classical method, with the near field first to have a first idea of how it behaves, then you tackle that with the far field method to get a deeper physical comprehension, and at the very end you add this lambda vector layer to have a final fine comprehension of the physics. So you really need the three methods each time you perform an analysis. So it is application. This again a 3D case that you can find in the Epsilon website. It's a rectangular wing with an AK-12 airfoil, and basically I'm computing point by point the lambda vector, or more precisely the lift contribution at each point due to the lambda vector. And this is integrated, of course, at each section to provide the lift at each section. And then, of course, when you integrate that, you obtain the lift distribution, and if you integrate the lift distribution, you obtain the total lift. As you can see, the lift distribution is similar to the near field and far field cases. You have a constant value that decreases toward the tip, and then you have a local sudden increase in lift due to the tip vortex. So the three approaches have delivered a very similar lift distribution. So regarding lambda vector, let's summarize its strengths here. First of all, it provides a physical interpretation of the forces that's very, very easy to interpret. Once you understand how to interpret the equations, you can directly apply this interpretation to the physical analysis, and that will give you a better understanding of the physics. It's also very easy to implement in CFD codes. You have all the parameters. You just have to take care of the numerical accuracy, and that's all. It also allows you to determine very rapidly lift and drag. So this is a very good application method. As I mentioned before, regarding the weaknesses, this is prone to numerical errors because you have to integrate vorticity inside the boundary layer, inside the small volumetric region around the airfoil, so you really need to compute that in an accurate manner. So this is a very important problem today that's currently being developed to solve that. So there are formulations under development. It's not as mature as a far field method. As you realize, maturing the far field method has taken almost 100 years. Instead, lambda vector method has started on the late 70s, early 80s, so it's not yet as mature as the far field method, but it will give you anyway a very good physical analysis. So I really suggest you to getting involved in this method and to try to implement this method each time you perform analysis, because even though it's not that accurate from some applications, it will help you to understand the physics behind, and that's very, very interesting for design purposes. And the problem is that only suited for CFD. That's a real drawback. We cannot implement yet lambda vector method for wind tunnel testing because we cannot measure lambda vector on the entire volume surrounding an arbitrary body measured in wind tunnel testing. So this is unfortunately a problem because we cannot validate experimentally our findings in CFD. So based on what I said before, it's not yet useful for design purposes, but however, it will give you a lot of elements to perform an extra analysis that will complement the other methods, and that will bring you the ultimate aerodynamic analysis method. So, having said that, at this point, we have shown all the three more used methods that are near field, far field, and lambda vector. More recently, let's say year 2000 or so, there's another method that appeared that's known as power balance method. And the difference of this method is that this time we are no longer using momentum conservation. We are using this time mechanical energy conservation. Let's see the details in the next slide. So this method appeared in a period in time where the aircraft configuration has changed. Just until the end of the 90s, the typical aircraft configuration for transport, for civil transport aircraft, were of tube and wing type. In those cases, the engine is separated from the airframe. And in those conditions, we can apply this equation, that is the Breguet equation. We can clearly separate thrust from drag, simply because the stream tube that crosses the engine do not interact with the airframe. So thrust and drag are quantities that can be determined in a univocally fashion. They are not. There is not an ambiguity in its definition. So you can apply this equation. You can do the design as we know to do. But what happens when it changes? Well, this is the case that I mentioned before, the tube and wing, where the engine is separated from the aircraft, and the airframe, you can compute its drag. For the engine, you can compute thrust, no problem. But what happens when you have a complex configuration? When you have more integrated configuration like this here, a BLI, boundary layer ingestion, here you can no longer talk about drag or thrust in a unique manner, because there are some ambiguity, some arbitrary definitions to do. It's not that simpler. So in this scenario, you can no longer apply the Breguet equation of range. And that's why when we start developing BLI configuration, we start realizing that all the previous methods, near field, far field, and lambda vector, were not well suited to study this kind of configurations. And that's where this method, the power balance method, come into play. Basically, this method allows to overcome this ambiguity in definition and thrust and drag by simply using the momentum equation that's used by near field, far field, and lambda vector, but this time the momentum equation is multiplied by the local velocity in order to compute the local power. So instead of talking about thrust and drag that are forces, we'll talk now about power. The power that is dissipated at the boundary layer, the power that is injected at the flow by the engine, and so on. So we change the reference frame. We change it from the force to a power reference frame, and that changes everything. That allows us really to generate a model that allows studying such a configuration, simply because we have to take into account just the sources of power, that is all the fans that are introducing power to the airflow, and also you have to take into account all the losses of power, that is the loss of power at the airframe, the loss of power at the nacelle, the eventual loss of power at the hub of the fans, and so on. So by doing this balance in the power that we are injecting respect to the power that is being dissipated, you can analyze such configurations, and that's the basis of the power balance. You're just doing a balance between the source of power and the power dissipated at the airframe of the body. That's all. That's the basic of the power balance. So that's all regarding the classical aerodynamic analysis method. Just a small reminder that you can implement all these methods with Epsilon. That's an open source aerodynamic analysis tool that can be used with ParaView. Basically, you can load your CFD or wind tunnel data, and then by using our specific custom developed filters, you can implement the methods that has been presented in this presentation. So that's all regarding the classical methods. In our next presentation, we will tackle the exergy method.